All right, welcome back. Time is now 2:10. So I'd like to bring forward Anish Anthony of Concurrent Real Time. He will be giving us a talk on real-time rapid control prototyping and HIL testing, hardware in the loop testing. Anish.
Hello. Thanks, Chris. And can you see my screen?
Yeah, we can see you. We can see your screen.
Awesome. Hello, everyone. I want to thank the Flight Software Workshop team for organizing this event. I represent Concurrent Real Time, and I've been at Concurrent Real Time for over 10 years. Before that, I was working at the MathWorks. I have a background in control systems and modeling simulation and real-time hardware in the loop testing. Although the topic of my presentation is generic, I'm going to talk about a trending topic on using real-time systems with GPUs for rapid control prototyping and testing. I will demo a workflow and show how easy it is to prototype and test a Simulink model on one of the smallest real-time systems that is running Red Hot Linux, which is the NVIDIA Jetson Nano. Concurrent real-time has been providing hard real-time solutions for over 50 years. And for the past 20 years, we have been focusing on bringing real-time to commercial off-the-shelf hardware and open source Linux. Our primary markets are aerospace and defense, and automotive is catching up. The goal of my presentation is to share with you the concept of real-time simulations and testing, and how easy it is to incorporate real-time testing into your product development process. Our real-time solutions are based on commercial hardware and easy to use and familiar open source Linux operating systems. We also provide higher level frameworks to help engineers easily use models written in C, C++, Simulink, or other modeling packages to simulate, test, and validate their applications in real time. Real time has a lot of different meanings, and I want to make sure we are all on the same page when talking about real time. I am talking about the keyword determinism. Take, for example, I have a Simulink model on my screen here, and the sample time is set for 1 kilohertz. That is, every 1 millisecond, I need to sample the input from my sensors, do my calculations, and send the output to the actuator. Again, every 1 millisecond, I need to do that loop. The idea is to take your model and test it with real hardware. The hardware could be a controller, like an autopilot, or you could be simulating a plant model, like an electric motor. And the controller, it thinks it's talking to the real motor, even though it is talking to a computer in hardware in the loop. This helps you to prototype and evaluate new ideas and verify and validate your algorithms and your models, helping minimize risk and reduce costs during the development cycle. Let me show you an example. Okay, this is my team developing and testing the model for this tricopter. And individual teams are working on developing and testing the models at a subsystem level. Okay, the colored bars indicate the model execution time for each subsystem. I have integrated each subsystem, and I'm now running the real-time simulation. And what is my frame rate? It is 10 milliseconds. My loop time of less than 10 milliseconds guarantees that I'm able to finish my control loop and meet my goal of landing on the desired location. What happens if my control loop is occasionally unable to complete within the 10 millisecond time frame? So if I have some sort of non-deterministic operation, the tricopter may or may not be able to meet the goal in mind and may not land in the desired location. So now the question is, how critical is it for this application or this autonomous vehicle to meet the desired goal in simulation? Let me make it a little bit more challenging. We have some new assets in the field of vision. Now the vision system complexity has to increase, and it is going to take more time. It is going to be more compute intensive, as shown by the gray bar, right? That's the vision system time. And I've introduced more complexity to my algorithm to track multiple objects. And now it is more critical to meet my goal. We continue to develop and test until we can guarantee in simulation that we will meet our control loop goal every time. And that is what Red Hat Linux and concurrent real-time help you achieve. Testing early, testing often, and testing enough is a huge part of the agile software development lifecycle and also of model-based design process. You see that rapid prototyping and hardware in the loop simulations covering the design V from concept to test and validation all the way up to production. We are not limited to HIL, but X in the loop, right? So we have software in the loop, hardware in the loop, driver or a pilot in the loop, artificial intelligence in the loop, processor in the loop. When we start our design process, we probably have nothing. We have probably plant and controller models either written in C, MATLAB, or Simulink, and we are running simulations. As we move along in the development, we will be replacing our models with real hardware as it comes online and test each and every subsystem with the real world and incrementally test our software with the real hardware until we are able to meet our goals. Concurrent real-time provides a full ecosystem for real-time simulation and testing. Our software and hardware teams are involved in the entire process. So our teams start with the COTS hardware, which is commercial off-the-shelf hardware, and we do in-house open development on our operating system, which is the Red Hat Linux operating system. We also have higher level applications like Simulation Workbench, which help engineers, not worry about the intricacies of real-time operating systems and how to work your models in real time. And higher level application tools will help you meet your real-time simulation needs. We also work at the IO hardware level, all geared towards real-time simulation and testing. Today, I'm going to cover 3 of these blocks. Basically, I'm going to talk a little about the IHOC, which is the high performance real-time computer platforms, and Red Hat Linux, which is our real-time operating system, and Simulation Workbench, which helps an engineer easily run models in real time. We support the latest and greatest hardware that is available, including GPUs. Just in December, we tested and benchmarked and delivered to a customer NVIDIA's latest A100 GPU for running CUDA code in a real-time loop for predictive control. Yesterday, in some of the talks, software security was discussed, and Red Hat Linux supports the latest options, including secure boot and TPM, which is trusted platform modules. Not only do we support the Intel and the AMD hardware, we also support the NVIDIA hardware, which is widely used and is gaining popularity in the artificial intelligence and autonomous vehicle development space. We have a good partner program with NVIDIA and some of its partners, and you can see some of our partner rugged systems, which are used in aerospace and defense. Of course, if you are tracking GPUs, they are not rad hardened, but there is still some research going on at NASA and other sites to use GPU on space applications. So this is something which is not, in space right now, but people are looking into it. Moving from commercial off-the-shelf hardware to our real-time Linux operating system. The Red Hat Linux team does a wonderful job of ensuring the compatibility with most popular Linux distributions out there. Our team takes the open source kernel from kernel.org and the user line from CentOS or Ubuntu or Red Hat and add real-time constructs to create Red Hat Linux. Again, this is just a subset. So if you have a particular distribution in mind, it is very easy for us to support it. And we are continuously targeting, looking at what our customers demand, and we add support for that. So as you see, software which works under Linux works with Red Hat Linux. So we have QEMU. We saw a couple of people talking about that. And that runs under Red Hat Linux. So it's very transparent. Shrink wrap software, which runs on the other Linux platforms, runs on Red Hat Linux and provides you the real-time capabilities. We add around 800 to 900 enhancements to the Linux kernel. And one of the primary enhancements we make to Linux is called CPU shielding. As the name suggests, for a multi-core system, we shield the CPUs and memories from interrupts, local timers, and other processes. So these interrupts don't interrupt your algorithm or code which you wish to run in real time. So in this example, I'm showing you a dual socket system which has 24 CPU cores. The typical systems we've been selling last year is 24 to 32 cores. And this year, like I've been looking at systems 48 to 64 core CPUs. So again, CPU shielding will shield your CPUs, which allow you to run your algorithms or models which are biased to the shielded CPU to run in real time. Anything which is already running on those shielded CPU will move to unshielded CPUs so that your process gets the full bandwidth of the CPU and the quickest response time to the required interrupts. In this example, I have, if you look at CPU core 23, I have a process P running on CPU 23, and I also allow the process to be interrupted by the timer T for the quickest response possible from your algorithm. Now that we have seen how one of the key features of Red Hat Linux, let's go to higher level application software, which is or a framework for running your real-time hardware in the loop simulations. And that's called Simulation Workbench. Typically, algorithm developers or modelers, they do not want to worry about the hardware aspect. Hardware engineering teams are completely different. And so how easy it is for a modeler or a algorithm development person to take your models and run it in real time, I'll show you using Simulation Workbench. So this example, I'm going to show you a workflow for Simulink models because Simulink seems to be quite popular. So what Simulation Workbench does is separates the model physics from the IO. Simulation Workbench is 12 to 13 years old. And we learned early on that once a model is validated and certified, there is no touching it. So if an analog channel stops working and you have to use a new channel, you cannot touch your model. So in case of Simulation Workbench, what we have done is we have separated the model physics from the IO. The workflow is simple. Create a real-time shared memory database for variables in your Simulink model. And then inside Simulation Workbench, map these real-time database variables to IO. And because they are running on Linux, on shielded CPUs, we leverage all the real-time constructs that Red Hat Linux has to offer, and your Simulink model is going to run in real time. Here's a quick overview of the Simulation Workbench frame. Last talk by Don Iles, we saw a frame of 2 seconds. So exactly similar to that, we have a SimWorkbench scheduler frame. And at the center of which you see is your Simulink model. It could be C++ model or from models from other modeling tools. And then you have the memory resident real-time database. And in order to talk to the real world, you have on the left side, you have the input devices, and on the right side, you have the output devices. So the entire Simulation Workbench frame is broken up into 4 subcycles, which is the input cycle. And as the name suggests, during the input cycle, we are going to take the data from the outside world and then throw it into the real-time database. There is an optional test script cycle. Basically, this is a way of manipulating what your model is seeing. So if your analog device is giving 3 volts, and I want to see how my Simulink model is going to react if it gets 20 volts, I can do that here. And then we have the third subcycle, which is the MATLAB Simulink or custom model cycle, where you take the data from the database, process it, and create the output, and put it back into the real-time database. And the fourth subcycle is the output cycle, where you take the data and send it out to the physical world. So all of this is taking place in real time. And Simulation Workbench, at the same time, you can look at your plots and your trends. And if you can see, I don't know if you can see it, you can see that all these different processes are running on different CPUs. And because we have all these CPU cores available, we can parallelize a lot of these tasks. A lot of the input can be parallelized, and you can get it as soon as the slowest task gets over. You can have multiple models, multiple Simulink models, or mix and match models to run in this loop on different CPU cores. I'm going to take the driving simulator as an example and show you how this real-time technology fits into the scene. Unfortunately, I cannot talk about examples in aerospace and defense because of all the NDAs, but everyone drives a car, and this example makes it easy to understand. Now, below the car seat, you will see that we have the real-time computer, which is simulating a high fidelity, 400 degrees of freedom vehicle dynamics model, along with a complex Simulink control system model. There is real hardware, which is, you see steering wheel, brake pedals, and also the ECU, which is the car computer. And this is all connected. You see ignition, injection, a throttle body, electric motor, because we are simulating a hybrid vehicle, and all of that is connected to this computer. So the ECU thinks that is talking to a real car because all the sensor signal that it gets from the real-time computer and the model makes it believe that it's talking to the real car. This is the way they test the models in real time, especially when you go into Formula One racing. The tracks change, the cars change, the setting changes every race, and they have to be very quick in prototyping and testing with the hardware in the loop setup. Simulation Workbench real-time database is what makes it easy, right? So at the center of it, we saw in the Sim Workbench scheduler frame how we use the Sim Workbench database, real-time database. And that makes it easy to connect. In this case, we have SimPack, which is the vehicle dynamics package, Simulink, and RF Pro is the scene generator, and the FPGA card, which is sending the signals to the ECU. All of these are communicating and interacting with each other using the real-time database. And that makes life very simple for engineers to mix and match different tools and technologies. Now I'm going to step into the demo. So for this demo, I'm going to show how easy it is to take a model in Simulink and run it in real time. The hardware of choice for me today is the NVIDIA Jetson Nano, which has a 4-core ARM, 128-core Maxwell GPU. But I also like to sometimes use the NVIDIA Jetson Xavier with the FPGA card as shown in the picture here, because that gives me super ability to mimic a ton of signals flowing in and out of my control system. So I can send and communicate with real hardware. So in this model, okay, so I have a Simulink model, which is an example of taking the raw, the roll, pitch, and yaw, passing it to a lookup table, multiplying it with a gain, and sending it to a scope. So it's a very simple model. In the real world, I expect the roll, pitch, and yaw to come from a real joystick. So the first thing we need to do is from this model is to simulate it. Of course, if we simulate it, make sure that we are passing a sine wave. I'm going through the lookup table and I get a sine wave. So the next piece is to, from the Simulink model, is to create my real-time database. Okay, so now I'm connecting from the Simulink model, which is running on a Windows or a Linux system, to this little hardware, which is the NVIDIA Jetson Nano system, right? So I connect, and that is where I'm going to run my, create my database. And so I choose what variables from my Simulink models are going to be in my database. And in this case, I choose blocks, the input blocks and the output blocks, which essentially are going to come from the joystick, and I create the database. The name of my database, simple_model, RTDB, create and upload it to the real-time computer here. And the RTDB is nothing but an ASCII file, and that eventually maps to a C structure, which is in shared memory. So you have the fastest access to it. So you can see I'm highlighting the ASCII file, so people can create the ASCII file for their own C code, where you don't have the ability to use MATLAB Simulink, right? And the next step is to generate code. All I did was select the button, click generate code. The amazing real-time workshop or Simulink coder tool will go and generate C code for your model and automatically put it onto the Jetson hardware and make it. So now we move on from Simulink to the NVIDIA Jetson side, right? So there we have simulation workbench running. And now what do? I have to take this RTDB and map it to real hardware. In this case, I'm mapping it to the joystick that I have physically connected to the device. And I'm mapping axis 0, 1, and 2 to the RTDB variables, which is. The next step is to create a runnable, which is I'm going to run this model in real time. So I'm going to select the RTDB and right click and say, I want to run my model. I can choose which CPU core to run because I have 4 CPU cores on the system. I'm choosing CPU 2. And then all I do is run the model. So as you see, it was very easy for me to take the Simulink model and move it to my real-time system. And because we are running in real time, remember I talked about CPU shielding. You can see the simple model is running on CPU 2, and I can come and say shield CPU 2, which means that no one else other than the tasks which are allowed to run on CPU 2 can come and interrupt my model running on CPU 2. And this is all happening in real time. Not only can I shield the CPUs, I can say for load balancing, I can say simple model, you are running on CPU 2, why don't you move to CPU 3? And it will move to CPU 3 because I say I'm running something else on CPU 2. And I can shield CPU 3. So now in this way, I can tune the system. Of course, you won't believe me, but I have a recording of having the joystick physically connected, and you can see the real-time charts as they move along. So as you see, it was very easy for me to take my Simulink model and put it for real-time testing. Because I can shield CPU cores, I can run Python code, non-real-time code. I can run different executives on the unshielded CPU and not affect the real-time performance on my shielded CPU cores.
1 minute remaining.
That was it. So not only can we take the model and run it in Simulink in real time, but also we can investigate and analyze and trace the model to extract the maximum real-time performance from the system. So in conclusion, we have a bunch of real-time tools and solutions, but we have a long history and we have excellent customer service and long-term program support. Some of your programs run for 10, 15, 20 years, and we do support programs long-term. And if you have any needs, want to know more, connect with us, join us in our kiosk or contact us, and we'll be glad to assist you and help you out with your real-time requirements.
All right.
That's all.
Thanks a lot, Anish. Very much appreciated.